We have been now looking at the spectral properties of line coded signals used in PCM systems. And yesterday we derived an expression for the power spectrum of such line coded signals. The general expression was, just to recapitulate what we accomplished yesterday, that a line coded signal which uses a pulse shape Pt with a Fourier transform P omega has a power spectrum given by this expression. Alright, where R sub i's or R sub n's denote the autocorrelation coefficients of the impulse sequence and in turn are dependent on the data sequence AK, the nature of the data sequence AK. So the important conclusion that we can obtain from this expression that we obtain is that the spectrum, power spectrum, or the spectral properties of line coded signals depend as much on the pulse shape as they do on the data sequence, or the other way around actually. Not only they depend on the pulse shape, but they are also dependent on the properties of these RIs, right? Depending on what kind of autocorrelation sequence the data sequence has, you may have a different feature, a different kind of power spectrum for the line coded signal. It is in fact this possibility of manipulation of the power spectrum through changing the properties of the autocorrelation sequence of the data sequence that we get different line coding schemes, right? Different line coding schemes, by virtue of the manner they exploit the relationships between ones and zeros and which ones are to be inverted and which ones are to be not inverted, will determine what the values of this RI is going to be, and in turn will control the power spectrum of the resulting signal that we finally transmit on the line, right? And we will see that it has a very important bearing and gives us a lot of flexibility in the design of line coding schemes. Now for the special case of on-off signaling, we went through this exercise a bit further. Now we are taking specific line coding schemes, and the first one we have picked up for discussion is on-off signaling. And by an appreciation of what these amplitudes R0 and Rn should be in this case, we could obtain an expression for Sy omega, which you must be having in your notes now, is given by sinc square function like this multiplied by this impulse train. Alright, this is what we could do yesterday. We finished the maths of this. Let's try to appreciate the significance of this mathematical result, and I will do so by means of this picture that we have here. If you plot this spectrum, well, from the mathematical expression itself you can notice that this spectrum contains two parts. This is a continuous function of omega, this part, right? The first factor of the spectrum is a continuous function of omega. It's a well known sinc square function, right? It also has a discrete part which consists of impulsive components, and it is a product of these two continuous and discrete components that we get the overall spectrum, which therefore looks like this. Each of these impulses by themselves is of constant strength and constant height, but after multiplication with the sinc square function, obviously their strength changes, and therefore you get an overall power spectrum which looks like this. this is the continuous part in this, and these are the discrete impulses, right. So the power spectrum of an on-off signal, mind if you remember also, this is the power spectrum of a return to zero on-off signal, right, in which we are considering a half width pulse rather than a full width pulse, right. So keep that in mind. So what we find is that the spectrum contains these discrete components at 2 pi by T0. The first zero crossing of this sinc square function occurs at 4 pi by T0. 2 pi by T0 corresponds to F0, F0 being the reciprocal of T0, and therefore F0 is the data rate, right. And 4 pi by T0 we have the first zero crossing, and therefore the main lobe width is how much? 2F0, right. But the interesting thing is,
4F0.
well, I am only including the positive part of it, right, because if we are talking of a baseband signal, the real bandwidth will of course correspond to only the positive frequencies. If it was a band pass signal, it would have been twice this much, but at the moment we are talking of simple pulses, baseband pulses, which are not modulating any carrier or anything, right. So this is a zero frequency over here. So the bandwidth of this signal is 2F0, and I will return to this point in a few minutes. More importantly, we find that we have discrete components at F0, which is a nice thing, right. Why is it nice? Because that means I have a specific finite amount of energy available at the clock frequency, right. The clock signal is being represented in the received signal, and I could use some kind of PLL of a phase lock loop to extract this clock component for synchronization purposes, right. This is a nice feature of on-off signaling, but other than this it hardly has any other nice feature, as we have already discussed. For example, its bandwidth is 2F0, which is very high, right. Why it is very high? We will see later that the theoretical minimum bandwidth with which we can manage to transmit data at F0 at a rate of F0 is F0 upon 2. Okay, we have not yet discussed this fact, but we will be discussing that soon enough later on. So with respect to the theoretical minimum possible, we are consuming 4 times as much bandwidth in the signal, right. Not very efficient from the point of view of bandwidth utilization, and that is a very important resource to worry about all the time for us. Similarly, we have already seen not only the continuous part itself has a non-zero value at 0, right, the continuous part of the spectrum, but we also have a specific discrete component, a very large amount of energy specifically present at DC, which we know is not a good thing to do. We have already seen why DC is not a desirable thing to have on a cable or any kind of line. We could reduce this bandwidth somewhat by using not return to zero signal but non-return to zero signal, right. Then we will be essentially using a pulse of width T0 rather than T0 by 2, okay. And what will happen to the main lobe of this? So if we go from RZ to NRZ, the bandwidth will be reduced by a factor of 2, it becomes F0, which is still twice the minimum that we can work with, but at the same time the only nice feature that this signal had will also go, right. That is, the impulses at this particular point, the clock rate will disappear, right. So, and also the clock signal, or I shouldn't really call it a clock signal, a clock recovery signal will also go, will disappear. That is as far as the spectrum is concerned. Okay, these are the broad conclusions that we can draw regarding the spectrum. Okay, there was one more point. We already noted that we have a non-zero PSD at omega equal to 0, right? And we have seen that that is not good, because that rules out AC coupling, right? We discussed that earlier. And AC coupling is something that we just cannot avoid in typical lines, in repeat at the places where we put repeaters. Why? We will need to use transformers, we will need to use AC coupling to remove biases that may be getting introduced by other circuits, right? So these kind of circuits are bound to be there in your line, particularly the points of location of repeaters, in which case we will have the DC wander on all those problems, right? Why do we require transformers? We require them for let's say impedance matching, right? We require coupling capacitors to remove any kind of biases that some circuits might be introducing, right? Therefore, AC coupling is something that is just not avoidable.
So what does DST stand for?
Or spectral density. Right? We are talking of S phi omega. So, and we also see that the bandwidth is excessive. We already seen that. Not only all this, in terms of its performance against noise immunity, it is less immune to noise, let's say, than the polar scheme that we will discuss soon again. Than polar scheme of line coding. Yes, please. Okay. It is less immune to noise than polar scheme, right? Let's see how. In a typical on-off signal, you will have two levels between, let us say, 0 and, I will just call it 2. Why I am calling it 2 is, I am comparing it with let's say polar signaling, in which we will have one level represented by, let's say, plus 1 volt, and the 0 level by a minus 1 volt, right? In order for both the signals to have same kind of performance against noise, it is clear that they should have the same kind of amplitude swing, right? So that a 0 is not confused for a 1 or vice versa due to occurrence of a large noise spike over a certain duration, right? Therefore, we should have similar swing. If this is going between plus 1 and minus 1, for getting the same kind of noise immunity, a on-off signal that we are discussing here, a unipolar signal, should have a swing from 0 to 2 volts. If this is going from minus 1 volt to plus 1 volt. Is that okay? Makes intuitive sense, and theoretically also one can show that under this situation they will have identical performance against noise as measured by probability of error, right? Probability of making a wrong decision from 1 to 0 or 0 to 1. But under these conditions, this contains twice as much power than this contains, right? This contains 3 dB more power than this. Let us see how. In on-off signal, because of the amplitude considerations, what is the energy of each pulse? It's proportional to 2 square. Let's call it 2 square E, where E is some constant, right? So that is the energy that's equal to 4E for on-off signals. Every time a pulse is transmitted, you transmit an energy proportional to this factor 4, right? Because the amplitude is 2. For the polar signal, on the other hand, what will be the energy transmitted every time a pulse is transmitted? Only E, because the amplitude is +1 or -1, right? So the value is E for polar signals. And suppose pulse duration is t0, whatever it pulse. Okay, let's assume maximum pulse duration, which can be t0. Then your average power in polar signal transmission is, let's say, average power for polar signals, because in every interval of t0 seconds you are either transmitting +1 or -1, right, and therefore you are transmitting energy E. The average value is E by t0, right, where t0 is the duration over which this energy is transmitted. On the other hand, for the on-off case, we are transmitting pulses only half the time, right, because for the other half time when you have zeros, you are not transmitting any energy, right. So therefore the average power calculation here becomes this, because only half the time you are transmitting ones, the other half time you are transmitting zeros, which are represented by zero amplitudes. So that's equal to, that's the average power for on-off signals or unipolar signal, which is twice E by t0. So what we find is that we end up transmitting twice as much power here, average power here, than we do for the case of polar signals, while getting the same noise performance, same noise immunity, right. So suppose you are interested in an error rate of 1 in 10,000, right. If for example, for this case, I think the corresponding figure is 8 dBs, you require a signal to noise ratio of the order of 8 dBs or 8.4 dBs. For the case of unipolar signal, will end up requiring 11.4 dB or something, 3 dB more power, which is not very good, because every dB of power adds up to cost, right, a lot of cost. Okay, so these are the various properties associated with on-off signal, both from the spectrum point of view as well as noise immunity and power efficiency point of view, right. These are in fact the two most important features to worry about when you're talking of line coding, namely power required for a given performance against noise and bandwidth used, and also whether it has susceptibility to DC and all those things or not, right. There are some other points to mention here. It also has no error detection or correction capability. Okay, it's not possible easily to correct or detect errors, and of course there is nothing in it which will help it to become what we call transparent to long sequences of ones and zeros, right. We will continue to have that disadvantage, that is possible loss of synchronization when there is a long sequence of ones and zeros. So this is called a transparency property. Okay, we would like line codes to be transparent to long sequence of ones and zeros, right, in the sense that our timing extraction circuit should not get affected if such a situation arises, and there is nothing in it which will help us to do that. So therefore, for all these reasons, on-off signaling is not a preferred mode of signaling, right. That is what we can appreciate, except for one, that it gives you, if you use half width pulses in the on-off signaling scheme, we get easy clock recovery, but that feature we can incorporate in other schemes also, as we will soon see. Let's then come to the second kind of signaling that we have talked about, go from unipolar to polar. in which a 1 is represented by some pulse pt and a 0 is represented by the negative of that, right? Right. That means your AK squares, remember we have to go to Rn's now to compute the, in every case that we consider here, we have to go back to the basic expression for Sy omega and look at the amplitudes R0, R1 and so on, so as to calculate the nature of the power spectrum. The P omega square part of it remains same, but the factor which depends on the amplitudes R0, R1 etc. will have to be calculated afresh depending on the kind of line coding scheme we have. So in this case your AKs are going to be equally likely to be plus minus 1, right? The amplitudes will be plus minus, either it will be plus 1 or minus 1, the strength of those impulses, right, in the polar signaling case. So AK square will always be equal to 1, no matter whether transmitting a 1 or a 0. Therefore your R0, you may recollect what the definition of R0 was, limit as t tends to infinity T0 upon T sigma AK square, right? This will be
1
into 1, which is always equal to 1. Similarly, what is the other quantity of interest? These kind of factors, AK into AK plus N, right? I think I am getting the habit of writing a bit small. Let me try to write big again. Same thing. AK plus N. This will be equal to.
So how do you get that T by T0 then?
For the same reason.
Summation AK square is 1.
The total number of pulses in the interval T is T by T0. For each of which AK square is 1. So after summing this up, we get the total value of T by T0, and that's how we get 1, right? Same argument that we use for on-off signaling, right? And this argument is going to be repeated every time we consider a new line coding scheme, right? Only the values will turn out to be different. Okay. All right. What is the product of these two? AK into AK plus N.
it can be minus 1
Right. We can have, because it's just ones and zeros at random, and which now become ones and minus ones at random, right? Therefore it is equally likely to be 1 or minus 1, each with t by 2 0 terms, right? T by 2 0 times each. Alright. So when you sum this up over k, what is going to happen? This is going to become 0. That means for any value of n, we can conclude that Rn is going to be equal to 0. N not equal to 0. Because for n equal to 0, we already seen it is equal to 1. Which means that the second term, summation term appearing in the power spectrum expression can be ignored. Remember this expression? Let me see if I can get it back here for you.
So why do we always assume that
this term Rn can be ignored, right? Yes. What is the question, please?
Why do we always assume that there are equal number of ones and minus ones?
Oh well, for one thing, it is convenient for the maths that we have that we are doing here. But more than that, in reality, we would like them to be like this. So if they are not like this, we will be converting our data to a form which makes ones and zeros to be equally likely. Because if you are not doing that, that means a lot of time you are transmitting redundant information. We will talk about that later when we talk about information theoretic aspects of what we want to transmit, messages that we want to transmit. It will always be preferred that we transmit digital data in a form in which ones and zeros are equally likely, right? If you are not doing that, you are not making the most efficient use of your available bandwidth. Okay, so we shall talk about that separately. It's a reasonable assumption. Of course, you may have a situation where in spite of your efforts, they don't become equally likely, right? Such situations are likely to be very infrequent and not to worry about too much, and we can obviously modify any of these results for that situation if required. Okay, let's return to polar signaling. So what will be your SY omega? It will be simply P omega square upon T0 into R0, which is 1, right? So P omega mod square upon T0. So no discrete component here, right? Unlike the on-off signaling scheme, we have no discrete component. It's only a continuous spectrum corresponding to the sinc square function if you use a rectangular pulse. So if you use a half width rectangular pulse, when I say half width, the implication obviously is half the duration that you can have in that particular interval, that is T0, right? T0 is the maximum duration, so half of that. So for a half width rectangular pulse, if you choose PT to be a half width rectangular pulse, your SY omega is going to be T0 by 4 sinc square omega T0 by 4. Okay, which is identical to the continuous portion of the spectrum of the on-off signal, right? This portion is same, and this is what it looks like. Ignore the solid curve here, we only look at this curve, right? This is the main lobe of the sinc square function that I plotted here only for positive frequencies, right? And it has its first zero crossing at 4 pi by T0, again corresponding to 2f0, right? The bandwidth required is again the same as that for unipolar signal, because the main lobe has the same width. Alright, I can reduce the bandwidth by a factor of half, again by going from half width rectangular pulses to full width rectangular pulses, right? But that's the maximum I can do, come from 2f0 to f0, right? And we'll talk about that in a few minutes. Now let's discuss the properties of the polar signal in relation to the properties of the on-off signals that we just discussed. The first point to note is that polar signaling, we have already noted, is more efficient. Than on-off signaling. In fact, it can be shown that as far as binary signal transmission is concerned, polar transmission is the most efficient in terms of power, right? Here I am referring to power efficiency. We can talk of power efficiency, we can talk of bandwidth efficiency in terms of for digital signals. Power efficiency refers to how much power is required for a given level of performance as measured by error rate, by a fixed value of the error rate, right? So if you specify an error rate, you calculate the power, and different schemes will have different power requirements for achieving their performance. A more power efficient scheme will require less power, and a less efficient scheme will obviously require more power. So polar signaling is more efficient than on-off signaling. In fact, it is the most efficient. We will see other line coding schemes also are less efficient than polar signaling, power efficient, as far as power efficiency is concerned. But other than the fact that it is more power efficient, it suffers from all the other disadvantages of on-off signaling, right? You may see that yourself. Suffers from every disadvantage that polar signaling has. For example, we have component at DC, even though it is not in a impulsive form, but the spectrum is, there is no spectral null at DC, right? Like no spectral null at DC. Which is preferable to have because of the AC coupling requirements we have discussed, right? Also, we continue to use excessive bandwidth, right? Agreed? Also, we are not transparent to long string of ones and zeros, right? And in fact, we seem to have one more disadvantage, that is, we don't have a clock recovery component present because there is no discrete spectral component at F0. But that is easily taken care of because if we rectify the receipt pulses, we will produce that, right? Because we will convert the polar signal into a unipolar signal. We can easily convert the polar signal for the purpose of clock extraction into a unipolar signal by simply rectifying the received signal, right? And then generating a component at F0, right? So clock component still recoverable through rectification. Okay, let me now write it because it will become too small. Any questions? Let me invite questions if you have any. Well, no problem. Let's say you're using half-width pulses. Right? That is your polar signal. Now if you want to convert to polar signal, all you have to do is rectify it, right? This will come here and you will get a clock component, right? That's the basic idea. In fact, you can only get a clock component like this provided we use half-width pulses. If you use full-width pulses, there will be problem. That is why we are looking at all these schemes with half-width pulses, because it is an important function to perform at the receiver and at the repeaters to be able to recover the clock. Although it's obvious that using half-width pulses will require twice as much bandwidth as using full-width pulses, right? We already seen that. We can always reduce the bandwidth by a factor of 2 by simply going from half-width pulses to full-width pulses in each scheme. But if we do that, we lose the flexibility of recovering clock through either directly or through a rectification process. Okay, so we'll keep that in mind. Yes.
So this is clear that why this polar is more power efficient than the on-off signaling.
Right.
But you said that intuitively the noise levels seem to be the same because the amplitude swings are same in both the cases, right? But before that you had commented that the on-off signaling is less immune to noise than the polar scheme.
Yes, the two statements are equivalent.
That is on account of power.
Yes, if you require 3 dB more power to get the same noise immunity, we say you are less immune to noise. Okay? There is no contradiction in that. Right? Any other question?
We go from half to full and then
Okay. You may ask the question here. You may direct the question here if there is a problem. Am I going too fast?
No.
You can slow me down by asking questions. That's a standard trick all of us can use, right? And that's equally true in a class. Alright, we next go to the third scheme that we discussed. What did we do from polar? How did we improve the polar? We went to bipolar, right? By using a scheme like AMI, right? which this bipolar is actually, if you remember, a 3-level scheme, right? And therefore we sometimes call it a ternary or pseudo-ternary signaling. For example, alternate Mark inversion is an example of this situation. In fact, that is the one that we are going to discuss here. This is more or less become a de facto standard for PCM systems. Till recently that was what it was. Even these days this is used quite often. And in this, a 0 is represented by no pulse or a 0 level, and a 1 is represented by either a pulse PT or minus PT, depending on some logic, right? For example, we may have alternate pulses to be positive and alternate marks to be positive and negative, right? Which is what we do in AMI. So really speaking, we have 3 levels. We use 3 symbols, namely PT, 0 and minus PT. Although we are doing binary transmission, we make use of 3 symbols, right? That is why we call it a pseudo-ternary signaling scheme, because in reality it is a 3-level scheme rather than a 2-level scheme. Alright, first thing I like to do is compute the PSD again, power spectral density function again, and we again start by looking at R0, which is given by the same expression as before, and we have to look at what will be sigma AK square in this case. Let's come to AKs. It's clear that in this scheme of things, half the AKs will be 0. If you are again talking of equally likely zeros and ones, original zeros and ones, then half will be 0.
Basically 1.
Very good. So AKs, half of them 0 and half 1 or minus 1, each contributing AK square equal to 1. For each of them, AK square will be equal to 1. The value that they will be contributing in that summation will be unity. So therefore, what is the answer? Do I need to compute? R0 is equal to half, right? Let's come to R1, which is limit t tends. You see the flexibility that you have now by changing the rules of the game. That is how AKs are related to each other. Successive AKs are related to each other in terms of positive and negative levels. You can do wonderful things to the spectrum, as we'll keep on seeing, right? So this is T0 by T0 by T AK plus 1. Let me consider first the case of n equal to 1. We'll discuss. In this case, we need to consider n equal to 1 differently from general n. Alright? Alright? Is it clear to all of you? Or you need to explain? Do I need to explain? Somebody has suggested that it should be equal to minus 1 by 4, and the answer happens to be correct. That means you can work it out. Right? Let's assume that you can work it out, unless you want me to do it. Okay. Very easy to work it out, because AK and AK plus 1 will have opposite signs, right? And when you have, we can have 4 possible symbols as far as symbols are concerned: 1 1, 1 0, 0 0, 0 1, right? Now in terms of level, voltage levels, this product will be minus 1 here, right? Because if one of them is 1, the other will be minus 1 in terms of voltage levels, and all the others will be zeros. So only 1/4 of the time you are getting a contribution from these terms, and that contribution is equal to -1, right, and therefore the result. All right, and for Rn, for n greater than 1, let's consider the situation Rn. Situation for n greater than 1 and the value of Rn. Okay, let us therefore start by discussing Ak into Ak plus n. Now, what can we have here?
1 by times 1 and 1 by times 1.
This could be 0 or 1 or -1, right, depending on whether one of them is 0 or whether both of them can be 1s or both of them can be -1s, or one of them can be 1 and 1 -1. You can have all possible combinations, and the situation is like this: 1 1 will give rise to either -1 or 1, right, depending on whether they both have the same sign or opposite sign. And then all the three other combinations again will lead to 0. That means the probability of a 0 is going to be 3 by 4. The probability of these two together is half, and each of 1 by 4, and each of them individually is 1 by 8, right. So therefore what is Rn?
0.
Half the time, 1/8 times they are 1, 1/8 times they are -1s, and the rest of the time they are zeros, right. So again 1s and -1s in this summation are equally balanced, right. So for Rn equal to 0 for n greater than 1. That means the terms which will matter now in that power spectral density expression are the R0 term and the R1 term, right. Is it clear to everyone? If necessary, I can go over it again if there is a problem. Fine. So what happens to Sy omega? We get P omega square magnitude upon 2 T0 into 1 minus, what is the value of this summation there? -1 by 4, right. So it is 2 sigma something, right. So that 1 by 4 becomes 1 by 2, which I have taken out, right. So you are only left with cosine omega T0. I hope all of you know which expression I am talking about. If not, let me recapitulate again for you. We are talking about this expression here, right. Substituting for R1, all the rest of the terms being 0, right. You get a -1 by 4 here, 2 by -1 by 4 is -1 by 2, which you are taking out. R0 is also half. Okay. Which you can write as P omega square by T0 using a trigonometric identity, sine square omega T0 equal 2, right. Now this is very, very interesting. Let us see in what way we have interesting results here. First, but before that there should be no mathematical problem. Anybody has any problem? Please speak out. First important thing to note is, irrespective of what pulse shape I have and therefore what Fourier transform is associated with that pulse shape, at omega equal to 0, Sy is going to be 0, right. So we have a spectral null guaranteed to exist at DC, which of course is intuitively obvious, because half the time we are transmitting ones and half -1s, and the rest of the time, well, they are all balanced. 1s and -1s are balanced, and the rest of the time we are transmitting zeros. So that is DC regardless of p omega, right? That is DC null is guaranteed, which is very desirable, as we already know from the AC coupling point of view. Now let us consider the case of half width. We consider a specific p omega now, half width rectangular pulses. For this case, your sy omega will be equal to, again that same sinc square function with width 4 pi by t0. This will become t0 by 4 sinc square omega t0 by 4 pi into sine square omega t0 by 2. Okay. Now what do we see? That's the second interesting property that we get from here. The first one was irrespective of p omega, we get a DC null. Right? What kind of p omega we might use? Now we are considering a specific p omega, namely half width rectangular pulses, which we have already seen in the polar and the unipolar case lead to a bandwidth of 2f0. Right? Let us see what do we get here. We get a bandwidth of, okay. You see, it is this factor which is going to make the difference. This sinc square function is going to have its first 0 at same point, 2f0. But this function has a 0 at half that point, midway between 0 and that point. I have drawn this somewhere earlier. Yes. Here is the spectrum of a bipolar signal. Right? You get a 0 at DC, right? And you get your first null not at 4 pi by t0 but at 2 pi by t0, because sine square omega t0 by 2 is 0 at this point. Substitute, what will you get? You will get sine square pi, right? Sine pi is 0, right? So the product of these two functions goes through a 0 over here. So your main lobe width is reduced by half, right? So the bandwidth requirement is now, for the same half width rectangular pulses, is not 2f0 but f0, right? Okay. So let me make this point very clear. The essential bandwidth, of course, you do, when I say essential bandwidth, the reason is there is still some energy in this lobe, right? Essential bandwidth is equal to f naught equal to 1 by t naught, which is half that of on off or polar, right, for the same pulse width situation. However, we are still off from theoretical bandwidth by a factor of 2. Remember that. Theoretical minimum that we can go to. So let's look at, in a nutshell, what are the advantages we are getting here in bipolar signals. We have discussed that earlier from an intuitive point of view. Now we are speaking from a very definite knowledge through analysis. First, spectrum has a DC null. Two, bandwidth is now, I don't think we should call it excessive. We are twice the theoretical minimum, but certainly it is not excessive. It's not 4 times that. Now what is more, these are desirable things. We are also somewhat transparent. Not, I think we are still not transparent to long sequence of ones and zeros.
So we transfer to long sequences.
Yes.
C3 we take care of.
To ones.
Yeah.
So we are not
So-
transparent to zeros.
We are not transparent to
String
zeros.
of
right?
Semi-transparent.
String of- So we can say semi-transparent or whatever, right? Translucent. Now, but we do have some other advantages. We have some error detection abilities, right? We can detect up to single errors. So we have single error detection capability. Can you see how?
Because alternate inversion.
That's right.
Violations.
If at any time you find that alternate ones are of the same polarity, that means you have made some error in the decoding process, right?
But how do you know that the thing which is coming, the next one that is in the alternate part, that is a 1. That could be a 0 which is cropped up on account of noise.
We don't. That's why we are not. We are saying detection. We are not saying we are able to correct, right? We are only able to say yes, there is an error. Nothing more than that, right? That can help you in some situations. All right. So there is a difference between error detection and error correction. And what about clock recovery? Okay, yeah, that's an important point. Do we have the possibility of clock recovery or not? Well, in the same way that we did for polar,
Same
right? Because I can always rectify it again and do it.
As long as the zeros are not zeros.
As long as, well, you know, that is taken care of by this property. That is a common disadvantage in all the cases, right? Even that discrete component that we talked about in the spectrum makes sense if you don't have long string of ones and zeros, right? Because that's assuming that your signal is statistically behaved, well behaved. We don't have long strings of ones and zeros, right? It's reasonably random. If it is no longer that random, that's why the transparency question comes up. If the signal is always truly random, ones and zeros are always changing, right? Then we'll always get the discrete component in the unipolar case. But even there we will not always get a discrete component if we get long string of ones and zeros. That is, if the signal is not truly random, which is implied by this kind of analysis. Okay. What about the disadvantages of bipolar scheme? Let's talk of power efficiency. Do you think it is as power efficient as polar or less power efficient than polar? Can you make any judgment?
Because
Why?
Same as
Power requirement more in bipolar.
on and off. Same as on off signal.
Just about as power.
Okay, the answer is correct. It requires again twice as much power as a polar signal does for similar performance. The reason is, now you have to distinguish, let us say, between plus A, if A is the amplitude of the pulse, and 0, or minus A and 0, right? Separately, as against polar, where I am comparing plus A with minus A, right? Here I have a separation of 2A. When I am making this decision again in the presence of noise, if I want same kind of performance, I better have the same kind of swing between 0 and this point, right? And not between these 2 points, because the choice is not between this and this, the choice is between these 2, and similarly the choice is between these 2, right? So the average power becomes again twice. Okay. Well, that's the main disadvantage, other than the fact that it is not fully transparent.
For full width pulse it will become 4 times
Uh,
power for full width.
no,
No.
we are doing a relative comparison. If they are full width here, they are full width there. If they are half width here, they are half width there. Okay? It doesn't make sense to compare two things which are not similar.
Noise performance should be same.
Right. We're talking of same amount of energy being transmitted in every bit interval, right? In whatever way you like to do it. Do we have time for? Okay. So we have discussed today 3 line coding schemes: polar, bipolar, and of course on-off unipolar, right? Out of which we have really gradually gone from the unipolar to the bipolar, and we have seen that we have considerably improved in our performance. And we'll do a few more things. We'll see that we can come up with some still better and nicer properties in terms of line coding properties, and we'll continue to do that tomorrow or next time. Thank you very much.